Question 26. A rod having coefficient of linear expansion of 1 times 10 to the power of negative 5 per degree Celsius and length of 70 cm has one of its end rigidly connected to another rod of length 1 meter and coefficient of linear expansion of 0.5 times 10 to the power of negative 5 per degree Celsius. Okay, so let's draw out a situation first, then after that we'll read the question. What are they asking for? So we have one rod which is 70 cm. Let's draw it over here. You have a rod which is 70 cm. So let's call it 0.70 meter. Then this rod here has a coefficient of linear expansion alpha of 1 times 10 to the power of negative 5 per degree Celsius. So I'm going to call this as 1 because I know this will be the first rod, there will be a second rod. So this first rod over here, it's rigidly connected to another rod of length 1 meter. So it means that one end of it will be connected to another rod and it's a rigid connection. It means by you cannot break it open. It must be stick to each other. Okay, so I'm going to represent it with another color, maybe green. So this another rod here, it's 1 meter. And it's rigidly connected to the first rod. Length subscript 2 is 1.00 meter. Then the coefficient of linear expansion, which is alpha for the second rod, will be 0.5 times 10 to the power of negative 5 per degree Celsius. So this is the situation we have here. We have two rods connected to each other. So previously they were at a certain temperature. Now they ask what is the new length of the joint rods when the temperature is increased by 30 degrees Celsius. So they experience a change of 30 degrees Celsius. So now it's 30 degrees Celsius higher than initial. So both of these rods here will expand. But because they have different coefficient of linear expansion, we cannot just treat them as one single rod expanding. We have to look at how does the first rod expand. We have to look at how does the second rod expand. We have to analyze them separately. Then we add them back up. Only we can find the new length of the joint rods. So the strategy is analyze them one by one. We see what is the final length of the first rod. We find what is the final length of the second rod. Then we add them up to find the final length of the joint rods. So that's what we are going to do. So I'm going to do it in one single equation. Yeah, you can do it separately and add them up. It's fine. I'm going to do it in one single equation. So we know that the length final will be equal to the length of the first rod final plus the length of the second rod final. Okay, you can call it L1 and L2, then you call the original length as L1 naught. That one is fine. Probably you should do that. That one is closer to what your syllabus use. Okay, so I call it L is equal to L1 plus L2. But I'm going to call the original length here as L1 naught and L2 naught. Sorry, it should be in green. Okay, so this is the situation we have. Let's continue to do our, we expand the final length for rod 1 and we expand the final length for rod 2. We know that rod 1 here, you can find its final length by saying that it's equivalent to the original length of rod 1, L1 naught, sorry. Length of rod 1 original times 1 plus alpha delta t. So alpha is a coefficient of linear expansion for rod 1. Delta t, you know that for rod 1 and rod 2, they are experiencing the same change in temperature. That's why I don't need to label them as delta t for 1 and delta t for 2. They are the same change in temperature. So for rod 2, you know that it will be equals to length of rod 2 initial bracket 1 plus alpha 2 because it's rod 2 delta t. Okay, so this is the equation that you have. You can continue to do your substitution. You know, the length of rod 1 is 0.70. 1 plus alpha, it's 1 times 10 to the power of negative 5. The change in temperature, some might be wondering whether you need to change to Kelvin or you need to change to degrees Celsius. Well, the idea is if you see what you're focusing on is delta T, you are focusing on change in temperature, then you don't need to convert. between degrees Celsius to Kelvin. Why do need? Because for change in temperature, 1 degree Celsius of change in temperature is equivalent to 1 Kelvin of change of degree Celsius. Okay, the delta T equals to 1 degree Celsius is equivalent to delta T equals to 1 Kelvin. If you increase a certain material by 1 Kelvin, it's equivalent to saying that you increase something by 1 degree Celsius. The change in temperature is the same. But if you're looking at it in terms of like temperature, okay, if you're looking at it as temperature, then you have to be careful. If you're looking at it as temperature, then you have to convert from that degree Celsius to Kelvin. Because let's say 0 degree Celsius is equivalent to 273.16 or 273.15 Kelvin. Okay, so this is the temperature. In this case, this is the boiling point. Okay, so for this situation here, because you're not interested with the change, you're interested with the actual temperature, the absolute temperature at that particular, for that particular material, therefore you need to convert it into Kelvin. So some examples is like if you are dealing with let's say heat conduction. Let me write it as example. Heat conduction dq over dt is equals to the negative of Ka dt dx. In this case, this is change of temperature, so you can no need to convert between degrees Celsius and Kelvin. Or let's say length is equals to the original length 1 plus alpha change of T. So in this case, you're only interested with the change of temperature. You're not interested with the actual temperature of the material itself. So you don't need to convert between degrees Celsius and Kelvin. But if you look at this kind of situation, let's say PV is equal to nRT. So in this case, you are caring about the actual temperature of the material. If you're actually caring about the actual temperature of the material, then you need to convert it to Kelvin. This equation only works when it's in Kelvin. Or it can be like P1 V1 equals to P2 V2. Okay, this one there's no temperature inside, sorry. Let's say P1 over T1 is equals to P2 over T2. So for this kind of situation, the temperature here is the actual temperature of the material at certain initial situation and final situation. So for that, you need to convert it into Kelvin. Okay, so the idea is you look at whether it's interested with the change in temperature. If it's interested with the change in temperature, don't need to convert between degrees Celsius and Kelvin, because 1 degree Celsius of change is equals to 1 Kelvin of change. But if you are caring about the actual temperature, the absolute temperature of the material itself, then you should convert it into Kelvin all the time, because all of our equations, if it involve the actual temperature, you should do your calculation in Kelvin. Okay, that's how you differentiate whether you need to convert or not. Okay, so we continue the change in temperature here. We don't need to change from degrees Celsius to Kelvin, so we just substitute as 30. Then we plus, original length is 1 meter, then it will be 1 plus 0.5 times 10 to the power of negative 5. Then the change in temperature is again 30. So now you have substituted in everything. I believe you get for the first part, first term over here, you get 0.70021. For the second part, you get 1.00015. So if you add them up, what you get is 1.70036 meter. So if you convert it back into cm, that will be 170.036 cm. So that's why our answer will be D. Okay, so in what situation can you analyze it as one single rod, even though they are made of 2 rods? In what situation can you analyze them as one single rod? It's when the coefficient of linear expansion for the 2 rods are the same. So if they are made of same material, 2 same material connected together, you can think of it as one single rod. But if they are made of different material, then they will have different coefficient of linear expansion. So in this case, they'll expand differently when they are subjected to the same change of temperature, but they will expand differently. In this case, you need to analyze them separately, independently, then combine them back to get the final length of the joint rods. So that's how you solve question 26. Let's move on to the next question. Question 27. A ball has a fixed volume of 5.10 times 10 to the power negative 3 meters cubed. So the ball is filled with air at an air pressure of 1.24 times 10 to the power of 5 Pascal and at a temperature of 25 degrees Celsius. So this is the temperature of the air in the ball at this moment. It's in degrees Celsius. We are interested with the temperature, not the change in temperature. You need to convert it to Kelvin later. Okay, the temperature of the air then drops to 0 degrees Celsius and the volume of the ball remains constant because it has a fixed volume, so the volume of the ball remains constant. Now they ask you to calculate the new pressure in the ball. So we have two ball here. They are not actually different ball, they are just ball in the initial situation and the final situation. So let's try to fill in all the information we have regarding the air in it. So initially, we know that this ball here has a volume of 5.10 times 10 to the power of negative 3 meter cube. Let's call it V1. V1, V in the first situation, the volume in the first situation. Then we know that the air in the initially should have pressure of 1.24 times 10 to the power of 5 Pascal. And the temperature is equals to 25 degrees Celsius, which if we convert into Kelvin, you should be able to get it as 25 plus 273.15 Kelvin. Okay, for the final situation, you know that V2 will be equals to V1 because the volume of the ball remains constant. Then you know that there will be a new pressure which you are asked to find, and the temperature, the new temperature should be 0 degrees Celsius. 0 degrees Celsius, if you convert it into Kelvin, that will be equals to 273.15 Kelvin. Okay, so now if you are asked, you have two different situations, they are the same amount of gas but under two different kind of thermodynamic state. What you can do is you can compare them using P1 V1 over T1 equals to P2 V2 over T2. So this comes from ideal gas equation actually. We know that PV is equals to nRT. So if we don't have any leaking of gas, we don't have any addition of gas, then we know that our N here should be constant. Okay, the number of mole of gas in the container should remain constant if there's no leaking or there's no addition of gas. Then you also know that R here is constant, is 8.31. So these two things here is constant. So if we bring N and R on the one side and we bring everything to the right hand side, so now we know that N and R is constant. Therefore, we know that PV over T must also be constant. Because if the left hand side doesn't change, then the right hand side should not change as well. So PV over T here is a constant. So if you compare it from one thermodynamic state to another thermodynamic state, you should be able to equate them together because this value here is constant no matter you're in different temperature, different volume, and different pressure. The PV divided by T will balance itself so that PV divided by T will always remain constant because the NR is constant. That's how you get this equation over here. Okay, so now we can perform our substitution. We know that the pressure, before we perform our substitution, there's one simplification you can do. You know that V2 and V1, they are the same value because the volume of the ball is constant. Therefore, what you can do is you can cross out V1 and V2 because they have the same value. You can just cross them out. They're on two sides of the equation. So now you're left with P1 over T1, the pressure divided by the temperature for the first situation, equals to the pressure divided by the temperature for the second situation. So what you need to do now is just substitution. 1.24 times 10 to the power of 5 Pascal divided by the temperature, let's call it 25 plus 273.15. Okay, so our pressure, we are asked to find pressure. So our new temperature is 273.15. So if you calculate, use your calculator, calculate, you should be able to get the new pressure to be 1.14 times 10 to the power of 5 Pascal. Okay, it's actually 1.136 something something something, but if you round it up, you get 1.14. That's why the answer is 1.14. It's a bit weird why we put 1.13 over here. Technically it should not be that close, but yeah, if you round it up properly, you should get 1.14. Okay, so that's how you solve question 27 using the concept of ideal gas law.